So, hello, dear students. I think we soon will start the lecture. So, I wanted to ask you, do you remember on which slide we finalized our lecture uh, previous time? So, unfortunately, I need to apologize because after the break on the last lecture, I forgot to turn on the recording sign. So, I only have the first half of the lecture recorded. So if you don't mind, then I have decided to start from this slide. Uh, and I'm just wondering, I guess we covered these multi-core uh, papers and this single core fiber paper. So I just wanted a little bit to remind about binary stream symbols and constellations and continue from there how different parts are done. Is this okay with you?
Yeah, totally fine.
Okay, but I don't remember which slide we find. Maybe we'll repeat some slides, but maybe that's good. Repetition is like mother of learning. So then let's start. So I'll start with recording.
Recording in progress.
So hello, dear students. So unfortunately, last lecture only the first half was recorded. So we decided to start with this slide. So as we know that. Uh, complex modulation formats like QPSK, 8PSK, 16 QAM, and higher orders allow us to transmit more data with the same speed. So it's the same symbol rate, and that's thanks to that we can assign uh, like in this example that we can assign 2 bits per symbol, and that's the case of QPSK. And then we have different types of symbols. Sometimes they are called alphabets. So why is that? Because then, for example, for some bit combination, for example, for 00, we can say that this is symbol B. And for 1, we can say that this is symbol A. And then we have A, B, C, and D. We have 4 symbols. And with 4 symbols, we managed to transmit 8 bits. So that's the main motivation of using complex modulation formats, since we can transmit uh, more symbols over the same bandwidth and more bits. Uh, right. Then there are different ways what could be used to transmit information with light. And what is currently being done that all degrees of freedom for light are used to transmit information. So here we have an equation where we have uh, electromagnetic wave. We have X polarization, Y polarization, and for each polarization, so for each polarization multiplex signal, we have amplitude, we have a phase information, and then we have also frequency division multiplexing or wavelength. So multiple channels could be used, or or carriers. Also on a single channel, you can use a subcarrier modulation. Uh, so yeah, there are different degrees of freedom. So all of these are used to transmit the information. And right. So I don't go too much more into details on an equation, but a typical component, for example, you have different polarization. So I think this matrix is important to remember, because we have I component, we have a Q component on each polarization. So for example, in case of on QPSK, I and Q both contains non-return to zero information, so 2 symbols in each, and then plus polarization. So that gives another way how to scale how much information we can transmit within the same bandwidth. Right. So what does it happen? So here is a bit of representation if we look on a constellation diagram. So some definitions that why we have this I and Q, and how do we define I and Q. So for example, in this case, there's a certain amplitude and certain phase, which leads to, for example, this constellation point with uh, this I value and this Q value on in here. So this is in phase or real part of a signal, and then Q part, quadrature, or imaginary part of a complex signal. So, and this is only for one polarization, and there's no time and space dependency. Right. Uh, and then you can see that every signal can be described with two parameters, amplitude and phase. And we can use both parameters to carry modulated can be modulated to carry information. So in this case, we both modulate both amplitude and phase, and then for example, in QPSK we have 4 points because we have one amplitude value, but then we have four phase values. Then we can add multiple amplitudes. Then we can get to 16 QAM and higher orders. Right. So maybe let's look a bit more in the details how that would look like. For example, for a QPSK, we could define four possible vectors and one vector position in the complex plane. So this is a complex plane. So we're working with complex signals in coherent optical digital communication systems. And here, this one vector is that you have phase up to here, and then you have this amplitude. That's one vector, and second, third, and fourth vector. So, and each of these vectors, well, when they defined, this is, I guess, cosine, and this is cosine, this sine. So sorry, the picture has been cut slightly. Uh, then you can see that each of these points. So here you have 0, 0, 1, 0, 1, 1, 0, 1. So in total, 8 bits, and that could be transmitted. So and then we can also define the symbols in some way that a symbol is when we have this signal. Then if we have opposite signal, then we have two zeros. Then we get somewhere here, and it's really related how much phase, what is the start and end phase of these symbols, and yeah, so which is defined by this rotation here, how much phase rotation is in there. And then we get I signal, Q signal, and so here I and Q, and then we get the end, what is the signal when we combine, and we get also a bit sequence and symbols for this. Right. So in case of QPSK, we have constant amplitude. Information is in phase. So amplitude. So this is why if you draw a circle, then you hit all 4 points. Of course, you can have QPSK have 8 PSK, and you can have also 2 PSK, or when you there are different ways, depends on how many phase values you look. And for example, for on-off keying, all the information is in amplitude, and then the phase there can be random. So in this case, phase cannot be random because it needs to represent the information there. Right. So therefore, for example, we draw 0 here and 1 here, and 1 can be on any place of this of the phase value, because in square law detection we don't really get the phase information. Also, Yeah. Okay. Um, then there's an example. When we talk about symbols and symbol rate and bits. So, for example, if we have uh, yeah, data rates is like really defined as bits per symbol or transmission rate. So, and we have original data like 8 bits, uh, and then we have of then these 8 bits can be converted and transmitted as 4 symbols, and then you get the symbol rate. Uh, so this is number of symbols transmitted per second. A unit is baud, and here is it's often called baud rate, but that is not completely accurate. When you call something which has a unit of baud, then it sounds like baud rate. So more accurate is to call it a symbol rate and use a unit baud. And then yeah, so then you can distinguish that in this case the baud rate is 2 times smaller than the symbol rate. Right. Okay. We already looked at this when we were looking into pulse amplitude modulation, where we had the 4 level, 6 level, 8 level symbols. Then we have also this definition of bits and symbols, and bits per second and bauds per second. Right. So there's then this is a very nice example which represents this, that we have the same optical spectrum here. Uh, so here you have for 2 bits per symbol, 4 bits per symbol, 5 bits, 6 and 8 bits. So we don't see a change in optical spectrum because optical spectrum, if we do Fourier transform from time domain to frequency domain, then what matters to set up a bandwidth is really the symbol duration, and that also sets up an optical spectrum here. I guess then some details like pulse shaping is used the same because that could change the shape of a spectrum. But here you see different examples of these constellation diagrams on complex plane, how they could look like when increasing number of bits per symbol. So most typically, what you will see in also in is QPSK 16 QAM. Then we start to see more fancy constellation uh, diagrams. And I think we will talk also a little bit later in the course about probabilistic shaping of these constellation diagrams. And because you can also choose how often you send a particular symbol, and there are benefits in terms of how much information you can transmit with a certain constellation point. Right, and as we already looked, that it's so typically for wavelength and polarization we use for multiplexing. So for polarization we use 2 different states of polarization: X polarization, Y polarization. And these polarization are so-called orthogonal. What does it mean? If you have 2 orthogonal signals, they do not interact. So you can use these orthogonal uh, signals as parallel data channels. And yeah, so this is what is used. It's like also when you use different wavelengths. So if the wavelength is separated and the signal bandwidth, they don't ever overlap between neighboring channels, then you also have independent channels. So you can use it for multiplexing. And modulation is phase and amplitude. Right. So here is another example of binary phase shift keying and how the time domain waveform looks like and how it looks like on compared to on-off keying. So in this case, we assume that the phase is stable for this on-off keying. Well, it can also be here, 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 and here, and here. But after detection, you will probably get it points like this. And binary phase shift keying is like switching between these two phase values. So phase 0 and phase 180 degrees. And then that you also can see when you look in a time domain waveform that in some moment the waveform switches 180 degrees and switches back when the change in symbols happen. But still you get so you get two symbols here and two symbols here. Right. But then if you, for example, use a differential phase shift keying, uh, then uh, uh, then you kind of get you need to when you detect it. So there's no okay, right. So for this part, we are gonna only look in when you modulate the phase, and then we're gonna move on when we add the amplitude. So for example, this one is like a detection. So when you have how could you do this in practice? That so we have not talked about detectors yet. Maybe I'll draw something that could allow us to uh, get to detect these signals. So you basically in the receiver you also use type of uh, it's a Mach-Zehnder interferometer. So here we have a one coupler, second coupler. Uh, Input output, and delay in this path is exactly one bit. So yeah, so this was used in the early days when you could use still a photo detector here. But then you needed to use this one bit delay, and then when you have once, then due to this delay, if the symbol is the same, it's constructive. If it's opposite, then it's destructive. And you see here there are quite a lot of opposite, and then again you have the same. You have a constructive interference. So interference process is used to recover information. Then it converts. This converts phase information to amplitude, which then can be detected with a photo detector, with pin photo detector. Right. So okay. Then the next part is that when we add not only phase but also amplitude to the modulation signals. So they're typical, commonly used 16 QAM, 64 QAM to 56 QAM. So you get from 4 bits per symbol to 8 bits per symbol. And of course, this is more sensitive to signal to noise ratio. So here you can use lower signal to noise ratio. Here you need to have very high signal to noise ratio. And that is why commercial systems, I think now they are trying to find a sweet spot of very high symbol rate is around 16 QAM. So because also that also depends how long link reach is needed. Right. Okay. Then so here again a bit of reminder about it's from the book. So we have covered this. Some constellation diagrams is IQ plane. I will not spend too much time on this, but here you can see. I think this one is pretty good that you can see that QPSK can also be called 4 QAM, and then you have a 16 QAM like borders of 64 QAM, and then just increase and you get more orders. So in between, for example, 32 QAM is looking like something like this. And between 4 QAM and 16 QAM, you have 8 star 8 QAM. So this 8 QAM can be made in different ways. So basically, it's eight points, and these points can be rotated in different ways to uh, yeah, so this gives so this is just the first example uh, where you can already start to think about geometrical shaping of constellation, because these outer points can be, for example, here and not here. And this one maybe is easier to detect, but we'll see. So we'll look in how you detect these symbols later on. Uh, Right. So and same thing applies here. You can have also these points. You could have them here. So instead of blue, you could have this red constellation, and it still would be the same. I mean, the difference here is that I have rotated this constellation by 45 degrees. That's it. Uh, right. Okay. Then what we could look also that there's a certain way how you can assign these bits to symbols. Actually, there's no general rule how you. I mean, there's of course. So uh, so for these square constellations, you can use gray mapping, and which again is that and that way. In that way, for example, if this one and this one are mistaken, then the difference in bits is only 1 bit. So for these 16 QAM, so square constellations, is possible to do gray mapping, and for others it's more challenging. And when you start to do yeah, so different styles of constellations, then it gets more difficult to use gray mapping. Uh, right. Then here is some examples for 8 QAM, how you could implement this gray coding here. Mm. So I'm talking about the constellations when we look at a circular QAM. So here you also see the same 16 QAM, 8 QAM, and already here also it's one more important thing to notice, that why some modulation format is preferred instead of other. So for example, uh, number of amplitudes when you use when you have signals, and the spacing between symbols is important, uh, and depends what type of impairment are you limited with. Are you limited with amplitude noise or with phase noise? So for example, in here in 32 QAM, so the spacing between the amplitudes is not even. So these symbols are more closely spaced. So this will create more problems with exactly these symbols which are more closely spaced. Then like for 16 QAM, they're equally spaced. So from a noise perspective, amplitude noise perspective, this is better. And also, when you have multiple amplitudes, then in a detection process, it becomes more complicated. Uh, right. So here are some examples. And as I mentioned, reach. So here we can learn a couple of things here from this table. So as you see that this table, the modulation order decreases and the maximum reach increases. Uh, so why is that? Because the spacing between these symbols is smaller, and if we have uh, longer reach, then we get accumulation of noise, and then nonlinear effects also start to play a more significant role. Then these constellations starts to get warped, and outer points get more rotated than the inner points. So it looks quite funny. I think maybe you can even see this in your Python simulations. Okay, then other thing is that we with higher order we can code more bits per symbol. Uh, and then there's a different examples of what is the symbol rate. So these symbol rates now I think for 16 QAM I've seen is beyond 200 gigabaud. So this is an slightly older table. And then this actually says, okay, for the symbol rate, what would be the how close these channels in wavelength division multiplexing grid can be put. So for example, for this signal, the grid is 50 gigahertz. For the 64 gigabaud signals, you need 75 or 100 gigahertz. And then if you have two, then it might maybe need more. So this just some standard rates and reaches. And for QPSK, it's 150 gigahertz, and then this gives kind of what is the efficiency when we spectral efficiency when we transmit the information. So, for example, it also decreases with the longer reach. Uh, right, and that's due to nonlinearities in optical fiber and also noise accumulation when you accumulate noise in in different spans, and after each span there's an amplifier which creates noise. But there's also other effects like laser phase noise and equalization enhanced phase noise, and these are we are gonna cover slightly later in the course. So yeah, so there are more impairments in coherent optical systems that needs to be dealt with to transmit information. Right. Then there's one more point. Here is like we already talked about these pulse shapes. Uh, so so we see we show a Fourier transform form of impulse response. Uh, and here is an example of frequency response that fits a rectangular spectrum window that fulfills Nyquist intersymbol criteria. Uh, So yeah, so then I think then we can look in different examples how we look like here how this uh, yeah. So when we look in time domain on pulses, I think we already had this for PAM. I think we covered a little bit about pulse shaping there, and here we see in time domain signal. And then we have a frequency domain, but this is linear and this is logarithmic. So with the higher roll-off factor, so you you decrease these side lobes quite significantly, and which means that you can put the next channel already here, not here. So that also gives you a possibility to increase your spectral efficiency here. So there are different parameters you can optimize for a pulse shaping. So here's, for example, alpha parameter. When you look in, how does it look in time domain with alpha 1 and alpha 0. And here you see alpha 1 and alpha 0 in frequency domain. It's a linear representation. There's also one more factor, which is this beta. So you get impulse and impulse response and frequency response. Here so these are the things one could optimize. I mean, so yeah, so this all is done just to increase the spectral efficiency, and it also impacts what type of modulation. So these pulse shaping can be optimized for every constellation order, and this actually affects where your beta rate uh, value, like how does your beta rate versus signal to noise ratio looks like, right. uh, okay, yeah, and also gray mapping also impacts that. How does it look like? Right. Then we have some other examples of on these pulse shapes. So here we have a 16 QAM signal. Then it's also we already looked at these in uh, pulse amplitude modulation scenario. Then this is, for example, for I or Q. And then we have optical spectrum outside how it would look like. So if you want to increase the spectral efficiency, then raised cosine with a roll of factor alpha of 0.05 is needed, because then you can squeeze more the same channels next to each other. Uh, what do you gain? What do you lose? You lose the eye opening in this direction, which means that your signal is less, sorry, it's more sensitive to timing errors. But you live with this penalty, and instead you can increase in this case the bandwidth that is required to transmit this, at least for the first lobes, it is 2 times smaller. And then you also don't have these side lobes which interacts with the neighboring channel. So that's a very tempting approach, and it's being used quite extensively. And this roll-off factor can be optimized depending on the system bandwidth. Uh, yeah. So okay. So here is some example how different modulations can be performed. So here we talked about uh, that we have a one carrier. Or there are questions in the chat. Let me just. So there are questions in the chat, so I can maybe bring them up if you see them. If you don't, so I mean, you can use different type of pulse shaping. So this is one commonly used, and there's one reason for it is that when you use a pulse shape, you want to use it for matched filtering. Uh, so you use a pulse shaper in a transmitter, and then you have pulse shaper in the receiver, and different filters could be used. So this is one of the most commonly used. Right. Of course, you of course you apply a low pass filter when you shape these signals. So it's related to match filtering theory in these systems. Hope this replies the question. If not, then we can maybe take it also after the lecture more. But it's good that you write these questions here. Okay. Uh, Good. And then when we have these when you have a single carrier and then modulated signal on it, there are different ways how to get information there. So you can use either you use optical carrier IQ modulation. So you have a baseband signal, and then you get it to optical carrier. But you can also have electrical modulation on RF subcarrier, and then you have optical carrier, and then you have two RF carriers on the side. So there are different ways how one could do that. And then you get in this concept of subcarrier modulation, and in this case you get 1 to 20 subcarriers, and they are RF generated. And what's the benefit is that these subcarriers can be pulse shaped, all of them, and then if you use the modulation format, then there could be less interaction between these subcarriers, and this is also quite commonly used in OFDM when these orthogonal frequency dimension multiplexing subcarriers. So one carrier to another is orthogonal. So there is again, so there's no interaction between neighboring subcarriers. So we can put them very close here. But you can also use wider carrier bandwidth here as well, and that's also been used quite. Uh, quite a lot. Uh, right. Okay, but then this is uh, this is like in frequency domain when we have these. Sorry, this is still big. So here you kind of see that you could have in frequency domain subcarriers like this, or with OFDM you will have subcarriers like this, and they don't interact with each other. Uh, Right, and then here you can see that how it would look like. For example, in frequency domain, then you do a transform, then the signal looks like this for different frequency. It's a different frequencies, and then you kind of sum them up, and then you do again for a transform, and then in frequency domain you have a different channel, different waveforms here. Right.
Excuse me,
So,
sir.
yes.
Here is the answer why we use sync function, because on the every interval the value is always 0. If you go back to this slide, yeah,
Yeah,
here,
for OFDM, yes.
Yeah, if we see if the frequency domain, the each interval is crossing at the 0 points, so it doesn't make the interference symbol problem in the transmission system. That
Yeah,
is why we use sync function.
yeah, sure.
Yeah.
Uh, Good. Thank you for the comment. Then, then here is again some representation of OFDM, how it looks like with different subcarriers in optical spectrum, and then yeah, and then for each subcarrier, you can define a constellation, and the good thing is that when you use OFDM, then you can use these. Then you can use different constellation order for each subcarrier. Uh, so, and for example, if here you have ideally very flat channel, then you can use the same constellation order for everyone, every subcarrier. But then you can also use this principle called bit and also power loading in OFDM signals, so which allows to increase the capacity even more if you have a like bandwidth limited system. But it's widely adopted in radio systems, in digital coherent optical communication systems. OFDM is thought to be too complex. uh, because yeah, the implementation seems to be complex, and then these subcarriers are not that narrow. So what we can see, there's digital subcarrier modulation based on with wider subcarriers there as well. Uh, right. Here is also a comparison between what filter length is needed and what is the spectral efficiency and peak to average power ratio. So so spectral efficiency, right? In some regions, you can get better than Nyquist pulse shaping here. But I think the big problem is that this peak to average power ratio is much higher in OFDM than with Nyquist pulse shaping. Right. So I think this is important to remember that I mean having high peak to average power ratio is not good in a communication system, even though in radio systems it's used quite widely, the OFDM uh, signals. Right. Then I think we start to look in modulation part of the signals. Uh, so I think before we go into this, I think I suggest that we take a short break, and then we are back in 5-6 minutes. Right. So.
Recording stopped.
So are you back? Let me just turn back the recording.
Recording
Okay.
in progress.
So can we start?
Yeah.
Yep. So here is also a bit of good graph to understand why average peak to average power ratio very high can lead to problems. Like if we have you have average power, which is it's a value, and then you have peaks of power which goes pretty high. So then you will start to get nonlinear impairments due to the modulation. So here's an example of transfer function of a Mach-Zehnder modulator. It's a sine wave function. So when we want to do modulation, then we try to use linear range. So here you see that the top, this part starts to get slightly nonlinear in the top. So this will affect how equal the distances will be between the symbols. So here we see it's one for example I signal. So in this case it's 1, 2, 3, 4, 5, 6, 7, 8 levels. So PAM8 is used to generate 64 QAM. So you have 4 times the symbols of 16 QAM. So you see here is 16 points. All right. So and then you kind of and this is already uh, a transfer function in amplitude, and then you get depending on this voltage you apply. So we have a zero voltage, and then you have a positive signal part, negative signal part, and the spacing will be dependent here. I would I mean, in practical systems, you may try to use everything, and sometimes you use this nonlinear part here uh, to clip away some of these spikes in the modulation from top and the bottom. Right, and then you can this is done with one amplitude modulator. And in IQ transmitter, you have one amplitude modulator, then the second amplitude modulator. So one is for I, the other is for Q. And then you get another phase modulator because you need to have a 90-degree between I and Q just to be able to form an IQ constellation. So you need to rotate the constellation. So here you have a I constellation, they have Q constellation, and then in that way you will be able to build. So maybe I'll just draw some example. So here you have a. I'll just draw a like on of king constellation. Here you have one constellation like this. That's in this point, and in this point you also have a constellation like this. What happens after this modulation that your constellation looks like this, and in that way you are able to build a constellation like this here. If you don't do this, then you probably have two amplitudes which you sum up together. Right. And we were gonna look in different ways, different impairment modes that it's very important when you design these IQ modulators because the delay in I and Q also needs to be quite matched, and also this when you amplify the signal which you put on these electrodes, it also matters that these signals are exactly the same. Right. But in real life, they're not exactly the same. So Therefore, this digital signal processing is needed to compensate for different impairments. Right, and and then you can also use this dual polarization modulator, where you use two IQMs, and so what happens here is that you have a IQM for one polarization, IQM for other polarization. What happens in practical systems that these are two exactly the same IQMs and is the same laser. So in order to achieve orthogonal polarization, you need to apply rotation to one of these channels. So in this way, you will have two orthogonal outputs. So yeah, here you have if you put this one here, then this polarization is here like this here, and only after this rotation you get polarization like this. Then you have two orthogonal polarizations at the output. And it's also easier to design the transmitter if you can have two exactly the same IQ modulators here, and you can use the same laser. So you don't need to have a laser where you rotate the polarization. In principle, you could rotate it here, but then the waveguide design might be a bit off. So yeah, this is more practical way to design these transmitters. Right. Here is a little bit about what happens in this lithium niobate. It's one of conventional materials which is used to create this modulation here, and so here you can see how these how different phase coherent looks like. I mean, here's again power transmission function. Again, from example, we've seen this, and here is also how much voltage you apply and what happens with the refractive index. So if you apply more more voltage, then the refractive index will have a larger change in the material. So in this case, so here we see a power transmission in a Mach-Zehnder modulator. And when we talk about intensity modulation direct detection systems, where we work with intensity, then there's a difference between modulators. If you look power transfer function and amplitude power function transfer function. So here this one is for power. So you have a quadrature point and you have a null point. So if you look at the when you have amplitude only, then you kind of have transfer function which goes down here and then goes up here. Up here. So then when you do the modulation, so when you perform modulation, then it's linear in amplitude. You kind of choose this bias point. So then you see that you modulate the signal in amplitude using this linear regime. If you look in power, then you're actually modulating, you bias in 0 point, and then you modulate between these two quadrature points. So then you don't get a linear modulation in power. So and that's important to when you compare different modulation formats. It's important to understand whether you are looking at the power transfer function or at amplitude power transfer function. And here's also one more important point is that when you operate an IQ modulator, then in power you operate at the lowest point. So, for example, if you put the light here as input here, and then you tune the bias. So in these electrodes, then when you apply an power here and change the bias, at some moments you will get maximum value, and some moments you will get minimum value. So in typical IMDD systems, you basically care about quadrature point where you put where you have the most linear regime. In IQ modulation, you have to go to zero, null point in power. Then you know that you are in the middle for the amplitude, and and the problem there is that it's already inherently has a lot of insertion loss. Like in amplitude modulation, sorry, when you use intensity modulation only, then you can lose half of the power, like 3 dB point. But then you need to lose more power if you go to 0 point. And that's leads to more insertion loss inherently in coherent optical transmitters. Right. So right, so so then yeah, then there's mentioned. I mean, for coherent optical communications, Mach-Zehnder modulators integrated with lasers are a key component. That's a fact. Right, here is again a slide just to define different voltages. So this is for QPSK and DQPSK. So we can maybe skip this one. So here is some modulation where when we apply different voltages to a Mach-Zehnder. Then we could have it also when we look at QPSK signals. So here is uh, more components in a transmitter. It's not only this IQ modulator, but it also you need to have electrical amplifiers, driver amplifiers, which provides this electrical signal here. Right, and some demultiplexer which converts binary stream to IQ data. Right, and then there are different architectures how one could implement these IQ transmitters. Uh, so here are different ways how you get there. So I think what we have not talked about is digital to analog conversion. So if you use optical or you use electrical DACs, or just the ways how you implement. So if you use all with optical components, this is very complicated optics and expensive. And then you kind of yeah. So there's also electrical way how to do this. But if you combine these signals in this way, then it's you get low resolution and not that flexible. Then you kind of can have an integrated approach. I think the most popular approach is how to get from bits to symbols is using digital to analog converters and driver amplifiers. And then you can also do quite a lot of signal processing already in a transmission, the transmitter itself. So and then the resolution is rather high for these digital to analog converters, right? So, and you can do multiple functions in here. So you can also use you can do pre-equalization. You can do pulse shaping, and you can also do like probabilistic shaping in symbols. So I'll just show on the next slide what do I mean by that. So, for example, here, this is 1, 2, 3, 4, 5, 6, 7, 8. So this is 64 QAM. And typically our constellations look like this. So this one is rotated, and then you can choose with a different distribution which symbols are transmitted more often. So for example, these ones in the middle are transmitted more often, and these ones on the side are not transmitted at all because the probability is very low. And there are different uh, distributions could be used, and yeah, and that depends on what type of impairments you have. I mean, one of most popular is this Maxwell-Boltzmann, and then you can also use exponential, right? But this needs to be optimized depending on every system, depending on nonlinearities and things in the system. Right. I think we already had this graph earlier. So, but here shows the importance of not only this geometrical constellation shaping what is done here with different geometries, but then you can get closer to the Shannon limit if you employ, for example, these probabilistic shaping here. Right. So an increase in this tiny bit of capacity is worth an effort because these are usually uh, deployed in undersea cables where you have a limited number of fibers. So every extra bit you manage to transmit gives you quite high revenue stream. Right. Then we've been talking about the modulation, but there's also other part is how do you get back to your bits from in a detector side. Right. So in principle, in direct detection, you get the photocurrent that provides information on the light's amplitude. And if you, for example, applied only photodetector, then you probably will get a constellation like this. So you get an eye diagram, something like this. So you get transitions, and you don't really get information about the phase here. So eventually you got amplitude square because a square law detector. So you are losing the phase information. So you need to do something with that. As I showed there was this one bit, one symbol delaying interferometer, which could be used. I mean, the principle is similar. So here, for example, you can mix the signal with the reference signal that allows you to measure the phase difference. So QPSK signal mixed with different reference signals. So you can only measure the phase difference. So for differential phase shift keying, it works. And the frequency difference shows up a linear phase change versus time. So it's also important that for this reference signal, that the frequency difference is not large. So in case of example I gave you with a one symbol delay interferometer, you have the same frequency because it's the same copy of the signal. So yeah, here you get reference, or you get signal and reference, and you mix them, and in this case the reference has both amplitude and phase frequency. So eventually, if you do the equation, you get both amplitude parts, and also you get phase part here. And depends in this configuration how high is your reference signal. So if you have a large reference signal, then you can recover on eye diagram. A small reference signal, there you don't get full, and if you have no reference signal, then you cannot recover the bits here, right? Then what you do in this case, that so in order, so here you only get half of the amplitude. I mean, you can improve that. If you, for example, you have a signal, you have a reference, you mix them, and then you have two photodetectors which you sum together, then you get 2 times higher amplitude here, which is also very good. So balanced, it's called a balanced receiver. So you get doubled intensity. Right. Okay, but then you still have this phase, right? So then we need to do something a bit more complicated. So for example, IQ demodulator, you have this term called local oscillator. So local oscillator is a laser which does not have any modulation on it. And then you use two balanced photodetectors. So you have two balanced photodetectors, one for I, other is for Q. And then here you also get a phase shift of 90 degrees. This part here is called an optical hybrid. Right. So then you can get amplitude phase. So you can measure amplitude and phase. You have I and Q components. So it's yeah, that's what is needed. Then if we look a bit more detailed, what we could do if, for example, we have two polarizations. So then our signal comes in. So imagine then we have a two signal polarization. So we have a signal which is where we apply polarization division multiplexing, and then the signal needs to be separated into polarizations. In practice, sometimes well, we need to rotate these constellations to know that we get full polarization, this X polarization here and Y polarization there. In practical systems, it's not possible to have a polarization controller here because you don't know what is the right one. So you need to have a feedback to tune it. It's not practical. So eventually it's done with the digital signal processing called butterfly equalizer, which does the polarization recovery. Right, but in principle, it's one IQ demodulator and second the IQ demodulator, and each for different polarization. And then you can get also equations here, and it's a good visualization that you can detect two different constellations and separate in non-return to zero signals. Here is also a bit more accurate design. So you have a signal, you have a polarization beam splitter, and here you only have a beam splitter, and then this 90-degree hybrid mixer, and then you get two balanced photodetectors uh, per each polarization. So we have four balanced photodetectors, and have they have two drivers per each polarization, I driver and Q driver. Right. Then there's one more thing which is important to know. There are different types of these detections that happen, and that is related to this local oscillator and signal. So signal is actually a laser light, which is modulated. And here is also a laser which is not modulated. So the difference between homodyne and heterodyne detection is that sorry. So for homodyne detection, we use these local oscillator and a carrier lasers. They have the same frequency. It's very difficult to achieve with two independent lasers. You need to do some injection locking or something, because there is frequency noise and phase noise in every oscillator. So in self-homodyne detection, you probably use the same light for transmitter, and the same, you split the laser and you use one in transmitter, other in receiver, but then you need to transmit the laser light on a separate fiber. So it was interesting approach in multi-core fibers, when you can use one of the fibers to transmit the local oscillator, and on other cores you can transmit information. Right. And then the heterodyne detection, when your local oscillator frequency or wavelength is not the same. So then you can have spacing. So this spacing, it's really defined by electrical bandwidth you have in the receiver. Typical heterodyne detection, I mean spacing, you try to keep as close as possible. But imagine you have two oscillators which are oscillating all the time in different with different phase. So it's very difficult to get the frequency difference zero. You can get it in order of megahertz, and that depends on how stable your laser is. And in practical systems, then you design semiconductor lasers which have a line width of like 100 kilohertz, and then depending on this kilohertz range, then the rest of processing is done in digital signal processing. So yeah, so you need to compensate for frequency difference and then also for phase difference. So it is quite many things to do in digital signal processing to recover the signals back. Okay. So as I mentioned, that you can also use this. You can refer signal to itself. As I mentioned here, that you have a signal and then you have this delay, and they have a balanced photodetector. So you can convert this amplitude modulation, so phase modulation to amplitude modulation, and detect it. You can try to do it with the several delays. So here is the possibility to get the differences in signals out. And if we look more detailed, so how it is done for IQ, so you get the 3 dB coupler here, 3 dB coupler here, and here. So you kind of put signal and the local oscillator. They are they mix together. And this is, as I said, this is this 90-degree hybrid where I have a 90-degree phase shift. And this is like your optical signal in input, and then balance photodetectors. Right. And then what is typically done then after these electrical signals, after amplifier, then you use analog to digital converter. So you have a DAC in the transmitter and ADC in the receiver. And then when you use this analog to digital converter, then you convert analog electrical signals in digital samples. And when you have digital samples, then you can apply digital signal processing. And we're gonna have one lecture where we're gonna look in different places of digital signal processing, but that will not be today. It will be one of the it will be a lecture in May. Right. So we already seen this measurement here, that you can do it for each polarization, right? And a little bit more with the equations here, how it looks like when you split the polarization. So you have a incoming polarization. Well, probably in real life is something like this, something rotated like that, or rotated like this. Oh, but for simplicity, we assume this case. So you get one signal, one polarization in one, another in other. So here you have a 45-degree polarization. So when you split this one, then this one splits into this polarization and that polarization. Is just how polarization beam splitter works. And right, so this is like circular polarization. Then you get two linear polarizations out. And you have two separate hybrids, and again you get I in voltage, and for each two different polarizations, and then you can digitize these all streams. And what is the benefit here? That when you digitize all these four streams, you have amplitude and phase for each signal, and then you can use all these four signals to do a joint digital signal processing. And that is the beauty of coherent systems, because you have access to amplitude and phase, and that gives also different possibilities mathematically what you can do with these signals. So and you can compensate for impairments in this way. Of course, your receiver and transmitter is much more complicated, so it makes sense to have this degree of complexity for long reach communication systems where you can compensate for effects like chromatic dispersion. To some extent, you can compensate for nonlinearities as well. So yeah, and different impairments in transmitter and receiver also can be compensated in digital signal processing. So right, I think we are slightly repeating. So here is an example of 28 gigabaud the dual polarization QPSK signal so we get 4 times 28 gigabits. Then the problem is that there is rotation of phase and polarization in a fiber, and then these polarizations are split, but then you need to do also quite a lot of signal processing here and after digital analog to digital conversion to recover this rotating phase and polarization in optical fiber. So Then you also get dispersion and noise from optical amplifiers. So fighting noise from optical amplifiers is difficult. If there could be a study that you can get rid of additive white Gaussian noise, I think you get the Nobel Prize quite immediately. But so in this case, fighting noise is just choosing a modulation format, like from as we saw this table earlier today. Yeah, this one that for a shorter reach, you get higher order modulation formats. For longer reach, you have a less complex modulation formats, which means that the here distance between symbols are much larger. So therefore, you can tolerate more noise in the system. So in the case of noise, it's everything is about how much noise one could tolerate. But that's not the case for fiber dispersion, because fiber dispersion can be compensated quite effectively in DSP, like phase and polarization as well. So there's also one more thing which we are not going to cover quite deeply in this course. It's related to forward error correction. So so effectively, you are transmitting 100 gigabits per second, which is 4 times 25 gigabits. Due to this forward error correction, you need to add parity bits. In this case, it's 3 gigabits per stream, and eventually you get you add extra 12 gigabits. So your data rate in the stream is 112 gigabits per second. The useful data out of it is 100 gigabits. So 12 gigabits is effect for their correction overhead used to compensate for errors. And here we need to come back maybe to beta rate curve we had like here. So when these coherent communication systems are operated, you quite often will see a FEC threshold. So which means that if you get the signal quality here below the threshold, that means that you can correct these errors down to, I don't know, 10 minus 12 or 10 minus 9. And that you count as error-free in your communication system. Depends on what is availability in this system. How many percent, how many beyond this 0.99995 or yeah, depending on data availability. Right. So yeah. So this overhead is widely used and yeah, it adds quite a bit of complexity if you look in well, what's the most power hungry part here is quite often the forward error correction, and these FEC limits they're different, and some use more complicated algorithms than others, so they're more or less power hungry, right? And then there's things what we do in different things. So I think we stop here because in the next lecture we are going to talk about how different in which in what algorithm is used to get back the constellations. So I think it's good to stop here today. Then I'm gonna stop the recording.
Recording stopped.
And then I give a floor to Daria. She wanted to give you more information.
Thank you, Oscars. Hello there, students. And I think I will share my screen and we'll talk regarding the practical works, of course. So I believe and I hope you have finished already the third practical work, and I really hope that you are working on your coursework as well. The deadline for the coursework is the 16th week. It would be the 25th of May, I think so. So I hope you are working on your courseworks as well. And today you will start working on the practical work number 4. Here is the description. The deadline is 18th of May for the report submission. And so the practical work description is pretty similar to the other previous descriptions and would be related to the receiver front end, the organization, and SQ. The similar topics you basically discussed during this lecture. Of course, it is based on the book, Digital Coherent Optical Systems by the early. I hope you are still reading the book and finishing the task. So you will have two, I would say, theoretical, analytical tasks. Only these two tasks from the section 4.4 need to be finished. And then you would have the Python simulations. You would have, this time you would have two codes to test. One is test modulation, and the second one is the test DSP core function. So the first one, you will be able to see and modulate the modulations like 4 QAM, 16 QAM, and 64 QAM. And in the second part, you will dive in to some DSP functions that are usually used in such systems to process signals after they're received. In this case, after they're received. So let's just go to the Python and look on the code. So of course you are able to access the Python code using this link. I've already opened the link and we will just go to examples. Okay, so the first code would be test modulation, and the second code you would be using test DSP car functions. Of course, the test basic, I already opened the codes, and here you can see the preview. So the most, and of course you will open it in Google Colab as I already did, and I run the first section. The simple thing I hope you just remember. So the most important thing, the parameters you would be changing would be the SNR value, signal to noise ratio in decibels, the order of the modulation. I just decided to test the 256 QIM modulation. As you can see, there are multiple options to choose from, which type of modulation to test. You are, of course, free to test other types of modulations. And if you decide to test multiple of them, yeah, sure, please add this to your report. This would be amazing if you decide to test more. And yeah, here you can see 256 QM modulation is quite dense, a lot of points. And here you can see the code prints out the bit error rate value, the SNR value. So in the task, you're asked to test the systems 16 QM, 4 QM, 16, and 64 for different SNR values, and see what bare values you would result in. I would highlight I would ask you to draw the bar graph yourself in, for example, MATLAB or which software it's easier for you to use. So basically we change the snare value and register the bar value, and just at this point you are able to draw the curve. And if you would draw the curve on the one graph, you would see what are the differences if we change the modulation format and how the system is resistant to noise in the channel. And you can, of course, draw your conclusions and analyze the graph which is needed in your report. And this code show, of course, if you have okay, let's try different modulation 16 QM. It will be just a bit easier to see. So of course you would get an error-free transmission and the first graph will show you how the bits are assigned to these symbols, and then you can see the constellation which shows the intensity, how often in which region the symbol is usually detected. I think it's just a similar graph as before, just inverted. If you would see from this variables, and afterwards you could see the color map, and then you can see it's unfortunate these colors are too similar, and you can see the regions from which the symbols would be detected. So this code will show you the approximate space from which the symbols would be detected. If we would decide to lower the snare value, for example, to 10 or 30, you would see that the symbols would be more scattered. And in these cases, we really need to draw the borders and make a decision. Is this point belong to this symbol or the next one? So you can try this code with different modulation formats, different SNR values, and please add your graphs and your findings, and of course your analysis to the report. So the second code, again, if we go here, so that's DSP car functions. And I have already opened in
Excuse
Google
me,
Code.
ma'am.
Yes, you have question?
Yeah, I have one question. Like
Sure.
in the last code, we have to like simulate this in the same parameters for different channels for the different SNR values. So
Mhm.
can we make a loop for these
Of course,
values?
you
Yeah.
can make any modifications if you are able to make a loop to draw the graphs automatically. Of course, sure, do it. It would be highly appreciated. You know, of
Thank you.
course, if you can make the modifications for sure.
Thank you.
You're welcome. Um, and okay, then to the next code. Here you could see the different examples how the DSP digital signal processing is implemented for different test cases, I would say. So for the first one, at the beginning, of course, these are just two signals, and then here we have um, mm, okay, the name is test sampling clock converter. You can see that the blue signal is, for example, the original signal, and then we have our, for example, received the orange signal, and you can see that in the beginning the samples are approximately at the same place, but then we have the mismatch. And when we're detecting and working, we usually need to lower these mismatches as lower this make this mismatches as low as possible, so we would detect our symbols in the correct spaces. So, and here you in this code, there are some examples and some different with the different signals how different DSP functions could be implemented. And here is just yeah, this is it. This is quite short code. This is the reason it was added in for this practical work as well. It's just for you to see how this P is implemented and how it is being used in with very simple signals because here you would have just the sine wave. Here we can see the example of quantization when you have these steps. Here you can see the clock, and here you can see just a shift between the signals, the delay between the signals, I would say. So you have different some tasks to finish in this part as well. You have I would say four tasks. The first one is just for you to describe the code, so I would see that you understand what you are working for, and some tasks regarding the different impairments. Here we have quantization, clock recovery, and some delays for E and Q components. So this is it for the practical work, I believe. You have any questions regarding the practical work? Number 4. Okay, then that is it from me for today. Thank you.
So then we are gonna stay here for a while and then see when the people are leaving. But if you have some questions you want to ask in private, so I will be still here. So then thank you all for today. You're free to leave.
Good additions.
Peace, level.